the kind of holy grail of computer science, if you want, is that you would just state the problem and then the computer would solve it for you. And this is a kind of like good old-fashioned AI, where you'd say to your house, I'm hungry, and food would magically appear in front of you. And so maybe we're moving towards that, right? But in some areas, and what I want to try and convince you today is that in the area of discrete optimization, we're getting close, or at least closer. So I'm not going to tell you that we can solve all discrete optimization problems. That's never going to be possible. We can solve a lot of complex discrete optimization problems very simply just by stating the problem effectively and then allowing specialized algorithms, allowing generic solving technology to then tackle that problem. And then I want to, sell my special sauce about how you do that. So what's discrete optimization? You've got a finite set of choices to make, and you've got constraints on those choices that hold. So for example, we saw a great example with Arno's talk about getting coverage and testing. That's a constraint that had to hold. And typically we've got an objective to be optimized, so we want to optimize the time for the test suite, etc. And ideally we'd like to get the best possible solution, which Arno was doing for some of his problems, or we would just want to find a good solution, because often in the real world, discrete optimization problems are too hard that we can ever actually find the optimal solution. And I hope that you just believe me that these things are ubiquitous in society. So discrete optimization problems are things like scheduling or routing, rostering, packing, right? They take part any kind of human activity, there's some kind of discrete optimization problem that's going on. And they're also ubiquitous in CS, right? So register allocation is a discrete optimization problem. If you're doing some symbolic execution, which we'll see some talks about later, then that's a discrete optimization problem. If you're doing clustering, that's actually a discrete optimization problem as well. So one thing I want to say is, this depends on your audience, but often I get this idea that discrete optimization is easy, right? So continuous optimization, now that is hard, right? Because in discrete optimization it's easy because there's only a finite number of choices to discover. So all we can really do is just try out every choice one by one, and then we can see which one was the best, and then there's the answer. And in some sense that's true, right? There is only a finite number of choices, but we've got to be very careful because this is about combinatorics, and those number of choices grow very, very fast. Right, so the example here is I'm doing traveling salesman by brute force. I can do a 20-city problem in 77,000 years, assuming that I can check 1 million permutations of orders to visit the cities per second. Maybe I have a fantastic Planck machine, right, which checks 1 permutation per Planck time. Then I can solve 48 cities in 1.5 times the life of the universe, right? So brute force, not going to happen. Now, if we talk about what you can actually do with traveling salesman, if you use the best known technique for this, you can solve 80,000 cities, right? So it's a lot bigger numbers than brute force. So how should we go about solving discrete optimization problems? So I'm going to suggest that what we do need to do, these problems are hard to solve, but how we can push that number from 48 to 80,000, well, from, let's say, 10 to 80,000, is by using advanced generic solving technology. And this can be linear programming or mixed integer programming or constraint programming, which we've heard about today, or SAT modulo theories or SMT style approaches, right? And for any of these approaches, basically we need an encoding or a model of the problem. And that's how we can solve these problems without knowing how, in some sense. If we can just write down a description of the problem and then allow this advanced solving technology to do the work for us, we can solve them without knowing how. Right, so when we have a real problem in the real world, then first we have to specify it, and then if we're just doing a normal kind of approach to solving these things, then I would build an algorithm specifically for solving that problem, right? That's a lot of manual hard work, and indeed this is often done. I would suggest that most discrete optimization problems are solved in this way in the world by doing some greedy algorithm or something simple like that. But we can go a different way. We can go this way where we'll take the specification, convert that into a model which can be understood by one of these solvers, and then automatically that'll generate effectively a program to solve that problem. And that's the difference in some sense. If you see in Arno's talk, he said, well, there's this greedy algorithm which is very effective, which we can do. It can solve very big problems. It doesn't give the optimal answers. So that was an example where the manual approach could be done very simply, but it wouldn't give you the optimal answer, and so you'd be paying a cost, a difference. Whereas the models, which he was generating, right, took a little bit more knowledge, but once they were done, then you didn't have to work out how it was done. Right, so here the big difference is, here you're talking about how do you solve the problem, and that's what you've got to concentrate on. You're building an algorithm to solve the problem, how, and here you're just saying, what is the problem? What is the problem that I need to solve? And so that's sort of the declarative view of the world, and I'd like to think that it's getting more and more traction as we understand, as we understand more and more complicated problems and how to solve them. This is the only way that effectively scales. All right, and this is the imperative approach, building C code to do something, or something, C++ code, whatever. And that has limits because now we've got, let's say, 50 years of people working on discrete optimization solving technology, right? And that's a lot to catch up with in your program. So in reality, what I'm going to talk to you about is MiniZinc, and this is a discrete optimization modeling language that we've developed over a number of years at Data61, previously NICTA at Monash University, and we've had a lot of collaboration with people, for example, in KTH, and continue to have problem and Uppsala. So here's an overview of the talk. I'll just give you some basics of MiniZinc, and then I was going to demonstrate the IDE, but apparently I can't plug my laptop in, so I'll talk about the IDE quickly. Depending on how time's going, I'll talk about functions just to show you some of the problems that actually come up. If you want to build a declarative modeling language which is expressive, then actually there's some interesting issues that arise, and talk about how we solve some of those. Talk about the tool chain of how MiniZinc solves and applications. Okay, so what's MiniZinc? It's this high-level solver-independent modeling language which allows you to write down the problem without committing to what solver or solving technology you're going to use. And then you combine that with data in this MiniZinc format, and that is compiled to a solver-specific program and then sent to the solver. The solver returns an answer, and then you can actually use MiniZinc to pretty print the answer if you wish. So just some brief history. So it started in about 2007, actually as a direct response in the constraint programming community to say, we really need a standard way of writing down our models. And since we'd been working on Zinc, which was indeed a generic modeling language, we built MiniZinc by cutting down Zinc into the smallest sort of usable chunk that we could get. And since then, we've been running a challenge every year where we have solvers enter, and they all compete against a set of problems. And I think this is useful for developing, for furthering the technology and understanding what's the best way to solve these kind of problems. So we reached v1.0 in 2009 tutorial, which was probably missing documentation. That's a problem always with research software. In 2011. In 2014, we basically released a complete new tool set. That's what I've been talking about. And 2015, we added some new features and indeed built a Coursera course which you can take if you want to learn about this stuff. And even today, we're adding new features to the language, so enumerated types. All right. So why should you use it? Basically, it allows you to do rapid expressive modeling, and you can try many different solvers on your model. Right? So if you want to try Google's OR tools, and you can use MiniZinc to do that. If you want to try G-code, a solver developed here, you should do that as well. And it's also easy for solver writers. That was one of the aims. So it's very easy to support MiniZinc because basically you just have to be able to read in a kind of flat form of the constraint problem, and you have to define how you're going to handle all the global constraints. And I'll talk more about the global constraints later on. It also gives you a conformance test suite so you can check that your solver actually solves correctly a whole lot of problems. So it's very easy to test and compare your solver. So let's look at a tiny example. So here's a graph coloring problem. I've got this graph of things. I want to color the nodes so that no two connected nodes have the same color, and the number of colors used is minimized. Right? So how many colors would I need? There's my quick question to the audience. Have a think about that for a few moments. All right, well, here's an answer. All right, I'm basically starting by greedy algorithm. I'll color one blue, then two red, and keep colouring like this, and I end up with 5 colours. And you can see that if I look at any two, I guess this is a pointer, look at two nodes that are connected, they've got different colours, right, every pair. So how would I write that in Minizinc? Well, here's the Minizinc model. So I've got two parameters, the number of nodes and number of edges, describing the data. So most of this is really just data. Then I'm just building up some names here of the set of nodes, which call them 1 to n, and the edges 1 to e. So these are just sets of numbers, 1 to e and 1 to n. And then for every edge, I'm saying what's the start node and what's the end node. So that's really just a description of the graph, nothing else. Then the decisions I had to make was colouring the nodes. So here's the decisions. Oh, so this is meant to, these are meant to pop up one by one, but somehow it doesn't like my thing. So that says colour under there, unfortunately. So here, for every node, we have to pick a number from 1 to n, which is the colour. And this is because we know that if we coloured each node by its own number, then we'd definitely have a correct colouring because no two nodes would be coloured the same. So we know we can colour it with n colours. And then here's the actual only, there's really two only interesting things of this model. The constraint, which just says for every edge, the colour for the start node of that edge is not equal to the colour of the end node of that edge. That's the colouring constraint. And finally, the objective, what we're trying to do is minimise the maximum colour we used. Right, so there's an example of a Minizinc model. Then we need to give some data, so we can express this graph here by saying, well, it has 10 nodes, it has 18 edges, and here's the start and end arrays, which give you, 1, 2 is that edge there, right? So if we look at this edge here, 4, 8, that edge there, etc. Right, and then we run those together, and then we'll get an optimal solution, which is in fact that we can do it in 4 colours. Right. All right, so let's look at the basic components of a Minizinc model. So we have variables, two kinds of variables. We've seen them already in this example. Parameters, which are fixed by the input, basically specifying what is the actual problem you're solving. So they were specifying our graph. And then decisions, right? And that's the key thing that you want are going to be decided by the solver. So in our example, that was the colour variables. And so we have integer decisions, of course. That's your basic discrete decision. And usually it's in a fixed range. In that example, all of our decisions were in a fixed range. We have enumerated types, which is basically just like examples in C, basically a way of giving names to integers, because no solver really understands enumerated types, but it gives you some type safety so that you don't use the wrong kind of object in the wrong place. We have Boolean variables, obviously, and that's the most fundamental decision. Is this true or false? And in fact, you can solve everything using Boolean variables only. Float variables, although this is not the focus, right, in discrete optimization, we need float variables to express things, but typically we're trying to solve problems where the critical decisions are integers, or about over a finite set of decisions. We're using floats maybe to represent something that's going on that has a continuous range. We also have set variables, so we can have sets of any of these previous types. Oh, this is the wrong version of the talk now, that's why I understand. Okay. I did upload another one, but obviously I've been started off on this one. All right, we'll go with this one. And see, because now I realise that there's a missing line here, which is we also have strings. They're not allowed to be decisions, but they're allowed for parameters. They're typically used for output. And we get multi-dimensional arrays of any of the previous types. And there's coercion from ints, enumerate types to ints. Basically, whenever you use an enumerated type, you can use it as, think of it as an int, and bools can convert to ints to floats. And then we've got our standard arithmetic constraints, right? Just standard arithmetic operators and integers and floats, the coercion, which would not be here if I was looking at the right version of these slides. Standard relations, and notice it's not just linear relations. We have not equals, as we saw in the example there, and then Boolean functions. So we can create large, complex constraints by joining these things together by Boolean connectives, disjunction, conjunction, implication, equivalence, etc., negation. And so how we actually generate things, and we've already seen an example of this, is effectively the key thing of how to generate constraints which are dependent on the size of the data, is that we have set and array comprehensions. So if you've seen array comprehensions or list comprehensions in other languages, you'll be very familiar with these. You basically have some expression and some generators, and here we've got a where condition, basically a test to say if you don't pass this condition, then you don't get anything. And you can use that to generate large chunks of data or constraints. So here, in an example here, if I S is 3 and N is this is examples for a Sudoku problem. So here's our Sudoku. We've got this puzzle array, which is what value is going to go in each of these positions in the two-dimensional array. Then this expression here is going to generate this thing here, puzzle 4-4, puzzle 4-5, puzzle 4-6, this list of all the possible values which occur in this 3x3 context here. And of course, in a Sudoku problem, we're going to force that those are all different. So we're actually setting this up for an all different constraint. And if we change A and O, these values here, so here's 2, 2, we can get the all different 9 subsquares that we have to build. And then the reason that we're building these list comprehension is for basically applying functions which apply to lists typically, or arrays. And so here is this constraint which is actually going to force that each of the 3x3 subsquares here has different numbers in it. So here's how I'd normally write it, right? I'm saying for all AO in 1 to 3, basically, then I collect these numbers and then apply all different to them. And indeed, this generator call syntax that we're doing here, so for all and then the brackets, is just a shorthand really for writing down the same thing. So you can see if we look at the middle part here, here's the original, the list comprehension or the array comprehension that we saw on the last slide. I'm applying all different to it. And then again, this is also a generator call. And really what I'm doing is building up a list of the values of that all different constraint and then applying a for all to them, which is basically forcing them all to hold. Right, so I can build large, complicated constraints and expressions using this kind of comprehension approach. If then else endif, if then else endif. So basically we often want to do things only in certain cases. So here, looking over my range, if I've got a start array, which is basically the fixed clues that I have in my Sudoku. And if there is a start array bigger than 0, so if it's 0, there's no fixed clue. Otherwise, I want to set the puzzle to that value. I can use an if then else endif. And it's always we always require an else because basically we always need to make sure that this expression has some value. Right? So if this condition doesn't hold, then this just results to true, and for all of true is going to have no effect whatsoever. And we can use this to build complex sort of output statements, for example. So here, the output is a list of strings which are going to be printed out. So you don't really need to look at this in too much detail, but this is basically what I'm going to do if I want to print out a Sudoku puzzle in a nice, beautiful form like that, right? So typically the way I'd produce a Sudoku puzzle, I have spaces, everything. This is generic in the size. Whoa, this is not that easy to use. That is, gosh. If S is 4, so I can do 16 by 16 Sudokus or 25 by 25 Sudokus. This will all work correctly as well. And one of the key things of modeling, one of the modeling power that comes from a constraint programming view of the world, although what I'm talking about, Minisync does not suggest what kind of solving technology you're going to use, is the ability to do array access on variables, right? So in Minisync, I can write an array. So here I've got a cost array here and a variable item which is indexing into that array. And this basically will give me the value of the cost for the item that the solver chooses. So this is very important for building complex constraints without doing, so if you're used to MIP modeling, you'll see often if I have 4 different dimensions to the problem, I end up with variables, 0, 1 variables with all 4 dimensions. But using this kind of array indexing, I can instead get rid of many of those dimensions and have much, much smaller problems. And that's useful and it shows up because in Minisync, this can also be a variable. So we can have if then else where this is a variable. In the original version of Minizinc 1.6, this had to be known at compile time. So in this case, start ij was given at compile as a data, so we knew which one of these would hold. But if start ij was a variable, then we need to work out what's the value of this expression given the decision that's going to be made by the solver about what start of ij is. And we can actually do that by basically translating this into this expression. So here, this is a little array of size 2. So here's the first answer, which is the else case. And here's the second answer, which is the then case. And then I'm looking up that array using this value, which is I'm evaluating this expression to see whether it's true or false. If it's false, it'll get 0. I'll add 1 to that, and so I'll look up the first element, so I'll get puzzle ij. If it's true, I'll get 1. I'll add 1 to that, I'll get the second element, which is start ij. So you can see that you can write quite expressive things once you have this kind of power. You can do the same thing. Well, we can also iterate over variable sets. So one of the things we have set variables like this one here. I might want to only have the color constraint occur. The two colors are different for some set of edges. So I'd write this very naturally by just iterating over the set of edges which are chosen. And in fact, this is very useful for defining complex constraints. And under the hood, this is what's happening, basically. It's actually being converted into an if-then-else, where we're actually giving this bottom or top value. We're iterating over all possible values for this edge set and only actually collecting a real constraint for when we're actually in this in the selected set by the solver. So this allows us to build very complicated constraints in a very natural way. But a key feature of Minizinc is the ability to write your own predicates, and this is sort of core to what's going on in the whole thing. So here, let's say in a scheduling problem, I'm defining a non-overlap constraint between two tasks. We have a start time and duration and a start time and duration. I can just write it like that. And then I can use that non-overlap wherever I want. And I can do some reflection to work out various features of, say, arrays, index sets of arrays, lower bound and upper bounds of variables to build complex constraints. Why is that important? Because one of the key features of Minizinc, or this view of the world, is the idea of global constraints. So, global constraints define combinatorial substructures that exist already. So we saw some examples of global constraints in Arno's talk, the n-value constraint, the GCC or global cardinality constraint. So an example is that the all-different constraint, which we've seen used in Sudoku, is actually encoding an assignment subproblem. So if I know that my problem has an assignment subproblem in, then I want to make use of that global constraint. Then the global constraint is really just a predicate from a Minizinc perspective. That's why predicates are so important. If I want to, I have other kinds of global constraints like cumulative, which is for a cumulative scheduling kind of subproblem. I've got bin packing global constraints. I've got packing global constraints, all these kind of things. And when I use them in my model, I don't know exactly what's going to happen to them, because depending on what the solver technology is underneath, it's going to be handled very differently. So the all-different constraint, for example, just forces that all the variables in an array have a different value. I could just be implementing it this way by iterating over the array and basically forcing a not equals constraint between each pair of variables that occur in the array. And that might be how my solver is handling it. Some solvers which only handle base constraints like this, that's the only thing they're going to do with an all-different constraint. I might have a solver that natively supports it. If it was a constraint programming solver, it would almost certainly natively support the all-different constraint, in which case, basically, the predicate declaration like this has no definition, and it will just go to the solver just straight as it is. Or I might be using a mixed interprogramming solver, which doesn't want this view. We could use this decomposition and then convert this. We want to linearize the constraint in the end. And I'd have a decomposition like this, which is basically saying, I look at all the possible values that this array of variables could take, and I make sure that for every variable in the array, the number of times, so this is like the n value constraint, the number of times that this variable takes that a variable xy takes a value d is less than or equal to 1. And this is making use of another built-in function here, which is basically converting an integer into an array of Boolean variables, right? So this, the fact that we have an all different predicate in our model means that we can, well, using these different decompositions, we can get different behaviors. So we can run the same model on very different solving technology. And so there's a comprehensive library in Minizinc with over 100 constraints. Not all of the ones in the global constraint catalog, which Arno talked about, because that's got a huge number of constraints, which are many of them not used that often. We tend to only have the most commonly used ones. Every solver supports its native library, and there's specialization libraries for if you want to use linear solvers or SAT solvers. And basically, this is the key concept between this model once and solve anywhere kind of idea. So another thing, just in order to make very powerful predicates, we also need this ability to introduce local variables into our constraints. So I can define an even predicate and basically say, well, this is a number x is even if there exists a y such that x equals 2 times y. I can also have local parameters here. So here I'm giving a lower and upper bound on this value y by basically taking a known lower bound for x and dividing it by 2 and a known upper bound for x and dividing it by 2. So this is static information that I can know it when I'm building the program. And that's going to give me a restricted value y. But there's an important restriction on local variables. They can't appear basically in a negated context like this, because if I write not even z, I'm basically saying for all y, x does not equal 2 times y, right? And the underlying solving technology that we use here can only really solve a conjunction of constraints, existentially quantified conjunction of constraints. All of these solving technologies, SAT, well, SMT, you can start to do some universal quantification, but basically most basic solving technologies do not support universal quantification. All right. So I did want to talk to you about the IDE, and demo it, but apparently there's complications in connecting my laptop. So basically there's an IDE which is small, lightweight, easy to use. It looks like that, no different from a normal IDE, but there's kind of examples of what Minizinc models start to look like in real-world examples. So this is an example of scheduling a port where you have to stack coal onto the port, and then it sits there for a while, and then you have to reclaim the coal onto ships when they arrive into the port. And in fact, the application does the stacking, the reclaiming. So it's basically a mixed packing and scheduling problem where all of this is done as a discrete optimization problem. And you can add JSON output, so you can, here's a little picture of a tiny bit of the stacking. You can see here's where we're stacking some coal, here's where it's just sitting there, and then we're reclaiming the coal. And you can see the movements or which reclaimer is doing this. So reclaimer 1 is doing this 2, reclaimer 2 is doing these 3, and moving around. In this example, we need that the reclaimers don't cross. So given the time, I don't think, will I look at user-defined functions? No, probably not. Let's skip through this. So I'll just briefly say that many things that you want to do in discrete optimization are actually building your own function. There's a functional relationship. Once I have this, then this holds. And you can see examples in the base language, like bool to int, which maps a bool to an integer, or min, or sorting, where I take an array of variables and sort them without knowing their values. And all different is a predicate example. And there are challenges in any language for modeling which has this, because you have partial functions. So these functions may not be defined in many cases, right? So if I just take min, if this variable set is empty, then there's no min, right? And I also have to be very careful about common sub-expressions, because what I don't want to do is build, what's going to end up doing is I'm going to build up lots of variables to hold the results of these functions, and I want to make sure that if I build the same expression twice, I don't write 2 copies of it into the solver. But I will skim through that, even though it's the technically interesting part. All right, I'll just show you the end thing, that basically, if we take our Sudoku problem, and we had our all different, now our all different defined for the mixed integer programming solver needed to make use of this function which mapped an integer into an array of Boolean variables, an array of 0, 1 variables, because basically a MIP solver can't have a linear model of this all different without this 0, 1 view of what's going on. And if we take out some Sudoku problems, some 16 by 16, so quite hard ones, and we run using our functional view of the world, then we've got translation time, there's a number of constraints. Here you can see that without this functional view of the world, we end up with 2 or more copies of some of the variables. And this is disastrous for solving time. So if you look at the solving time here, we get a nice, these are not very challenging problems for a discrete optimization solver, but sometimes we're disastrously worse because we haven't taken into account common sub-expression elimination. All right, so just to talk about how Minisync solves. So we take our model, and the model will make use of some global constraints, and there'll be a library specific to a solver that defines how those global constraints are going to be used. Then, of course, when we actually want to run, we're going to have some data specific to that model. Whoa, what's happening? Oh, that. Okay. This is the old architecture, but basically this is still the core of what's going on in Minisync. So then we're translating that model to a specific flat-zinc form, which is basically an input form for the solver, which is just variables and constraints and nothing else, an objective, nothing else, right? And then we can run our solvers on that. It could be all kinds of CP solvers, all kinds of MIP solvers, etc. And then we get some text output. And so that's the original way that Minisync worked. And the problems with it was text-based toolchain, this rather monolithic compiler, and a one-size-all-fits translation. So when we went to 2.0, basically we took our cue from LLVM. We said, okay, what's a modern compiler framework? Because effectively what we're doing is compiling models and data into programs for specific solvers, and we want to use the same ideas. So basically we've got an API-based approach to this thing and a very modular transformation, which can be easily modified so that when you add a new solver or when we want to improve the language, we can do that easily. So not text-based, not one-size-fits-all. And so this picture here basically becomes this one, where we have libmzn, and basically there's front end, so we can use it just the same as we did, pretty primitives of outputs, but we've got direct calls to the API. We can have an API from C++ or Java or Python directly into this. We've got translation passes, etc. And so this means that it's easy to build applications using this foreign language API and or extending the Minisync library. And so we can do the good old Unix style. So this is what you could do in the previous case, right, where we could take our application, we could spit out even the model maybe as text, a string basically, as a pipe that in, data, and the output pipes back. But now if you want to build applications, really more natural way is to maybe have a separate model here. You can actually compile that to C++ or Python or Java, basically a piece of code that you can link into your model, into your application, and then all your things can be done by direct API calls. You can also use JSON, so do data and output through JSON. It's very easy to build web applications using this style of thing. And so basically, I'll just go on about, so Minisync is an ongoing thing. It's fairly widely used. It's basically a de facto standard for CP modeling. But upcoming features include pre-solving, where basically we will send your model to a CP solver, in fact G-code, to reduce the size of domains of all variables and then actually recreate the output for a different solver. And the reason for this is it can make much, much smaller models. It's a bit like the pre-solving that Arno was talking about, right? If you can do some reasoning about this specific data, and that's exactly what G-code is doing here, and reduce the size of the model or fix lots of variables, and then send it to a different solver, like a MIP solver, then that's a big advantage. So half reification is about a better way of handling complex Boolean expressions that can actually make things A, more expressive, and B, faster. We have a beta version of stochastic mini-zinc, so if you want to solve stochastic discrete optimization problems where you have some kind of two-phase or multi-phase entry ability of knowledge and have to look at multiple scenarios, then you can do that directly. We've also got an extended search language, so I didn't talk, even though, so mini-zinc is designed to be solver independent, but you can send information to the solver through annotations, which allows you to control that solver specifically. So for CP solvers, for example, you can add a search annotation saying, I want to search in this way. It's currently fairly limited, but with mini-search, you can do quite extensive search possibilities. We're also working on variable strings. So string solving is very interesting for congolic testing and for looking at problems like security holes, where can I build a string which has this particular form, right, which will cause you to, so the user might be able to input some nasty string which pops out in the wrong place. So string solving is one of the things that we have now, a basic version of this. We've got some connection to nonlinear solvers, but it's not really the key. In some sense, discrete optimization is what it's focused on, but there are obviously more and more problems where we have a complex interaction between discrete variables and nonlinear and other nonlinear continuous variables, and that is important to have support for more solvers. Nested constraint programming is the ability to build actually problems where a sub-problem or part of the constraint that you're building up is actually itself a discrete optimization problem. So we can actually, we have a language for doing that, but it's not been integrated yet into mini-zinc, but where you want to, define, for example, to find a good Sudoku system, I would say, here's a set of clues. What's the minimum number of clues that you need so that there's only unique solution to the problem? That's a good Sudoku problem, right? And that's actually a nested constraint program, because I have to actually, once I pick which set of clues you want, I actually have to prove that there's only one solution, right? And also tuples and type constructors, things that we had in Zinc, which we got rid of. So to conclude, what I want to convince you to do is use mini-zinc, and indeed make all your benchmarks available in mini-zinc. There's now hundreds and hundreds of available benchmarks in mini-zinc, which allows you to look at how other people have solved problems close to what you're solving. And you can try out different solvers on the same model. And indeed, you can use one of our state-of-the-art solvers if you wish. They're very effective on many discrete optimization problems. And if final thing, you can do a Coursera course called Modeling Discrete Optimization. All right.
Thanks, Peter. And this time I don't forget the gift. Thank you very much. So, questions, anybody? Do you know of sorry? All right.
You mentioned that you use solvers like Gurobi and like Cplex. So
Yep.
I'm guessing this is not strictly for discrete optimization. You can handle like mixed integer.
Yeah, so you can handle mixed integer. We have the float variables, but it's targeted at that. And indeed, the point is, if we come, so we come from a CP background where we want to make decisions about sets and about lots of, sets as that's a combinatorial decision. So basically, it's targeted more at those problems. Now, mixed integer programming solvers can solve a lot of combinatorial discrete optimization problems very, very effectively. And in fact, they're the right technology for a lot of problems, right? But they're the wrong technology for a lot of other problems. For example, in scheduling, they're typically not competitive with CP technology. And so one of the aims of this whole idea is that you should not commit to the solving technology while you're building the model, while you're describing a problem, because it may be the wrong solving technology. So there are some examples of problems which might be very easy to express in MIP, but are much, much better solved in SAT or max SAT solvers, right? Even though you can write them down in MIP very, very simply, they're just the linearization. Basically, a MIP solver has to understand basically understands the linearized version, right? The continuous version, and it gets no intuition. So one of the examples is like for sports scheduling, for example, where you can write MIP models to do it. It's the wrong idea. What you should do is write down high-level constraints like all different, right? Because sports scheduling is full of all different constraints, and it's also often full of symmetric all different. Basically, you can write down your constraints at a high level. You can try the MIP solver, or you can try a SAT solver, and maybe you find out the SAT solver is much better. Or you can try a CP solver, and indeed, a CP solver with some techniques like lazy decomposition would probably, in overall, be the best technique for that.
Right, but then let's say you're writing a problem that, doesn't really fit within, let's say you write a MILP, where you do have some continuous variables.
Yep.
And then it's going to try to send it out to other solvers that really don't do continuous variables.
So the solver will basically, if it has no continuous variables in it, and that's certainly often that's the case, then the solver will just complain. Effectively, you'll send it to FlatSync, and at that point it'll say, I don't understand it, or there can be an error message basically when we see the output. That you can definitely write models which won't be solvable by some solvers, because not all solvers are able to support everything. But if you get rid of continuous, basically, you can use sets in solvers that don't support sets. You can use, right? So anything can be used to send to a MIP solver. If you stick in the discrete only part, then basically Minisync will guarantee that it produces a model that can be run by that solver, right? The floats is the exception because there are a lot of solvers which don't handle floats at all. But there are CP solvers, for example, which do, right?
Right, but then when it generates that model, does it tell you, let's say it takes away some parts of the model because that solver can't handle it? Does it tell you that, oh, actually, I'm taking away that feature because?
Oh no, so it doesn't take you away; it'll just stop.
Oh, okay.
Right. But there are also, for example, hybrid backends. So you've got hybrid MIP CP backends where you will send some constraints to one solver, some constraints to another solver, and you'll let an interaction between them to work out who should be doing what.
There was one more question from David.
Thank you. So a very nice, interesting, and clear talk. I think this is a good example of an external DSL.
Yes.
Okay. So you skipped over a little bit, of course, with the functions. So I was interested. Do you have recursive functions, and does it make sense?
We do have recursive functions, and basically you can. Ideally, original Minisync had no recursion, so it's not Turing complete, right? We added recursion because it was just so easy, it wasn't difficult to do, but the problem is the recursion has to be finite given the data. So it has to be recursion controlled by the data. Now, in a constraint logic programming system, for example, you can have recursion which is controlled by the solving, and you can express things that we can't express, right? But it turns out for the discrete optimization sort of focus of this area, you don't very often need that. You're often basically, once I've got the data, I know the sort of size of the problem. We have versions of Minisync or front ends to Minisync for planning style problems where that's much more interesting, right? Because typically you don't know how many actions you're going to have to do, and then you basically need a loop around. Basically, you need a way of extending the model and going back. But yes, recursion is there, but it's got to be controlled by the data. If it isn't, it'll just hit the stack limit and say goodbye.
All right, so let's thank Peter again.